The future of computing is often imagined as software, artificial intelligence, cloud platforms, autonomous machines, digital networks. But beneath all of it, there is silicon. And beneath the silicon, there is a machine so complex that only a tiny number of companies on Earth can build it. It does not look like a smartphone, or a computer, or a piece of consumer technology. It is a massive industrial system filled with precision optics, specialized components, advanced materials, vacuum systems, software, and engineering tolerances measured at almost unimaginable scales. Its purpose is simple to describe: project patterns onto silicon. Its consequences are not, because the smaller the patterns, the more powerful the chips can become, and the more powerful the chips, the more advanced the technology built on top of them. Artificial intelligence, supercomputers, advanced communications, autonomous systems, and the computational infrastructure of the future. This is extreme ultraviolet lithography, EUV, a technology that sits near the frontier of semiconductor manufacturing. And because the frontier of computing depends on it, the machine has become something more than industrial equipment. It has become strategic infrastructure, a technological chokepoint. The world may contain thousands of chip companies, but the ability to manufacture the most advanced chips depends on a much smaller number of systems. And when a technology becomes essential while its supply chain remains concentrated, engineering becomes geopolitics.
A modern semiconductor begins with a simple material, silicon. But silicon alone does not compute. The intelligence comes from the architecture created inside it: tiny structures, electrical pathways, transistors, and layers of circuitry. To create those structures, manufacturers use lithography. The basic idea resembles photography. A pattern is created, light is used to transfer that pattern, and the pattern is repeatedly placed onto a silicon wafer. But the scale is radically different. The goal is not to create a visible image, it is to create structures so small that millions or billions can fit onto a tiny piece of silicon. The smaller the features, the more transistors can potentially be placed on the chip. More transistors can mean more computational capability, more efficiency, and more performance. But there is a problem. Light has a wavelength, and the wavelength limits how small a pattern can be projected. To create smaller structures, manufacturers need shorter wavelengths. This is where extreme ultraviolet light enters the story. EUV operates at a wavelength dramatically shorter than the light used by earlier lithography systems. That allows manufacturers to create smaller and more complex patterns. But producing and controlling this light is extraordinarily difficult. The technology is not simply a better camera, it is an entire industrial architecture designed around the physics of light. And the closer the industry moves toward the physical limits of manufacturing, the more complex the machinery becomes.
Extreme ultraviolet light creates a problem. It does not behave like ordinary visible light. The wavelength is so short that the light is absorbed by air. It is absorbed by many materials, and it cannot simply pass through conventional lenses. This changes the entire design of the machine. The system must operate in a vacuum. The light must be generated, captured, redirected, focused, and precisely controlled. But conventional lenses are not enough. So the system relies on specialized mirrors capable of reflecting the light with extraordinary precision. Every surface matters. Every vibration matters. Every particle matters. Every deviation can affect the pattern being printed onto the wafer. The machine therefore becomes an engineering ecosystem, a light source, a vacuum chamber, precision optics, motion systems, control software, sensors, and thousands of components operating together. The challenge is not solving one problem, It is solving thousands of problems at the same time. The machine must generate enough light, maintain the required environment, move the wafer with extraordinary precision, align every layer, and repeat the process across millions of structures. This is why EUV took decades to develop. The technology required advances in physics, optics, material science, mechanical engineering, software, and industrial manufacturing. It is not one invention, it is a stack of inventions, and the machine at the center is the physical expression of that entire stack. The most important fact about EUV may be that the machine is not really one machine. It is a supply chain, a global network of specialized capabilities. One company may design the overall system, another may produce the light source, another may create the precision optics, another may manufacture specialized components, another may provide advanced materials, another may supply the software. Each part is difficult, but the real challenge is integration. Every component must work together, at extreme precision, under extreme conditions, and at industrial scale. This creates a technological ecosystem, a system where specialization becomes an advantage. No single company needs to manufacture everything, but every critical supplier becomes important. This is the architecture of modern industrial power. A complex product depends on a distributed network. But some components are more replaceable than others. Some have alternatives, some do not. Some can be redesigned. Some require decades of accumulated expertise. And some technologies have become so specialized that rebuilding the capability would take years. This creates a hierarchy of dependency. The final machine may be assembled in one location, but its capabilities come from across the world. The machine therefore represents something larger than a product. It represents accumulated industrial knowledge, research, capital, engineering, and supply chain coordination. The system is difficult to copy because the knowledge is distributed. And when knowledge becomes distributed across decades, a competitor cannot simply buy the blueprint. It must rebuild the ecosystem. The world is entering an era where computation is becoming strategic. Artificial intelligence requires advanced chips. Advanced weapons require advanced chips. Data centers require advanced chips. Autonomous systems require advanced chips. And the most sophisticated technologies increasingly depend on the ability to manufacture at the leading edge. This creates a strategic problem. Designing a chip is one capability, manufacturing it is another. And manufacturing the most advanced chips requires specialized equipment. The equipment is not universally available. The supply chain is highly concentrated. The expertise is difficult to replicate, and the production timeline is long. This creates a choke point. A country may have enormous capital, world-class universities, advanced software, and ambitious technology companies. But if it cannot access the machinery required to manufacture the most advanced chips, its ability to compete at the frontier may be limited. This is why lithography has become geopolitical. The machine sits at the intersection of commerce and national power. A technology company sees a manufacturing tool. A government may see strategic infrastructure. An engineer sees a technical achievement. A military planner may see a capability with national security implications. The same machine can be interpreted in completely different ways. And as advanced chips become more important, the technology required to manufacture them becomes more strategically valuable. The chip race is therefore not only a race to design better processors, it is a race to control the infrastructure that makes those processors possible. The semiconductor industry is one of the most globally distributed industries on Earth. The chip may be designed in one country, the software may be developed in another, the manufacturing equipment may come from another, the materials may come from several more, and the final chip may be produced somewhere else entirely. This creates a paradox. The industry is global, but its critical capabilities are concentrated. A single product can depend on dozens of specialized ecosystems. Each one has its own expertise, its own infrastructure, and its own strategic importance. This makes the supply chain powerful, and vulnerable. If one part fails, the entire system may feel the impact. The semiconductor industry therefore resembles a network of choke points: design, equipment, materials, manufacturing, packaging, testing, distribution. The system requires all of them, but the most advanced layer may be the most difficult to replace. This is why countries increasingly seek technological sovereignty, not necessarily by producing everything themselves, that may be impossible, but by securing access to critical layers. The question becomes, what capabilities cannot be allowed to disappear? Which technologies are too important to outsource completely? Which supply chains are too strategic to leave vulnerable? The answers are reshaping industrial policy, technology policy, and international relations. The semiconductor industry was once treated primarily as a commercial sector. Now, its most advanced infrastructure is increasingly treated as a strategic asset. In the past, geopolitical power often depended on controlling territory, resources, trade routes, and military infrastructure. Now, technology creates another form of strategic leverage: access. If a country controls a critical technology, it may influence who can use it, who can buy it, who can manufacture with it, and who is denied access. This changes the nature of competition. A technology does not need to be physically destroyed to become strategically unavailable. Access can be restricted. Supply chains can be regulated. Exports can be controlled. Companies can be placed under restrictions, and entire industries can be forced to redesign their strategies. This is the geopolitics of technological dependency. The country that controls a critical layer can influence the capabilities of others. But this strategy creates consequences. Restrictions can accelerate domestic development. Companies may search for alternatives. Countries may invest in replacement technologies. The system begins to fragment. Globalization becomes more strategic. Supply chains become more political. And technological efficiency is increasingly balanced against national security. The result is a new industrial environment, a world where the question is no longer simply who can build the best technology. It is also who can access the technology, who can control the supply chain, and who can survive if access disappears. A technological choke point creates power, but it also creates motivation. If access to a capability is concentrated, others will attempt to recreate it. The process is expensive, slow, and uncertain. But strategic dependency creates pressure. Countries invest in research. Companies build new facilities. Governments provide incentives. Universities train specialists. And entire industrial ecosystems begin to form. The goal is technological independence, but independence is difficult. A machine can be copied. A supply chain is harder. The equipment requires suppliers. The suppliers require expertise. The expertise requires people. The people require institutions. The institutions require time. This is why technological sovereignty cannot be created overnight. The system is cumulative. Every generation of technology builds on the previous one. A country may construct a modern facility, but still lack the deeper ecosystem around it. This creates a race, not only to develop new technologies, but to rebuild the industrial capabilities behind them. The race for semiconductor power is therefore a race for time. Who can develop faster? Who can train more engineers? Who can build the supply chain? Who can secure materials? Who can create alternatives? And who can maintain the lead long enough to make the next generation possible? The future of technology may be determined by who can move fastest through a system that takes years to build.
The EUV machine was not created as a geopolitical weapon. It was created to solve a manufacturing problem. How do you print smaller patterns? How do you build more advanced chips? How do you push computation further? But technology does not exist in isolation. As the chips became more important, the manufacturing capability became more important. As artificial intelligence accelerated, the value of advanced computation increased. As nations competed for technological advantage, the machinery behind advanced chips became strategic. This is how industrial technology becomes geopolitics. Not because the machine changes, but because the world around it changes. A tool becomes infrastructure. Infrastructure becomes dependency. Dependency becomes leverage, and leverage becomes power. The machine itself does not control the future, but access to the machine can influence who is capable of building it. This is the architecture of technological power. The visible product is the chip. The invisible foundation is the manufacturing system. And the deeper the technology stack becomes, the more important the foundational layers become. A company may build the AI model, another may design the processor, another may manufacture the chip, but the entire system may depend on equipment produced by a very small number of industrial ecosystems. This is why the most powerful position in a technology economy may exist far away from the consumer, not in the application, not in the interface, but in the machine that makes the entire system possible.
The semiconductor industry is often described as a race for faster chips, smaller transistors, more artificial intelligence, more computational power. But beneath the race, there is infrastructure, the ability to manufacture, the ability to supply, the ability to scale, and the ability to access the machinery required to push technology forward. Extreme ultraviolet lithography sits near the center of that architecture. It represents something larger than one machine. It represents the accumulated complexity of modern industrial civilization. Physics, optics, materials, software, engineering, capital, and global supply chains. No single company creates the entire capability, but the system only works when every critical layer works together. That is why the technology is so difficult to replicate and why the strategic value is so high. The future economy will require more computation. Artificial intelligence will require more chips. Autonomous systems will require more chips. Data centers will require more chips. And every new layer of digital power will increase demand for physical infrastructure. The digital future is therefore built on industrial foundations, and those foundations are not evenly distributed. Some countries design, some manufacture, some supply equipment, some control materials, some provide the talent, and some control the connections between them. This creates a new map of power, a map defined not only by borders, but by technological dependencies. The country that controls the most advanced chip design has influence.
The country that controls the manufacturing has influence. The company that controls the most critical equipment has influence. And the system that controls access has leverage. This is why the future of geopolitics will increasingly be written in supply chains. The most important strategic asset may not be a natural resource. It may be the ability to manufacture intelligence. The most powerful infrastructure may not be a military base. It may be the factory that produces the processors powering the next generation of systems. And the most valuable choke point may not be a narrow strait. It may be a machine that stands between the world and the next generation of computation. Because the future does not belong only to those who invent the next technology. It belongs to those who control the infrastructure that makes the technology scalable. The chip is the visible product. The lithography system is part of the hidden architecture. And hidden architecture is where power often accumulates. The world is entering an era where computation is becoming a strategic resource. And the race for that resource will be decided by the systems capable of building it. Next era, decoding systems, architecting wealth.